Welcome to another module in this massive open online course. So, today we will start talking about vestigial sideband modulation. Alright, so the next topic or next different form of modulation that we are going to be interested in is vestigial sideband. This is another form of modulation. We have seen single sideband modulation. So, this is vestigial sideband modulation, also abbreviated as VSB, vestigial sideband modulation. And we have already seen the motivation for vestigial sideband modulation, and that can be expressed as follows. Let me just remind you again why we need vestigial sideband modulation. Okay. So, let us consider a message signal MT. This is our message signal. This is our message signal MT, which has the following spectrum. Let us say MT has the spectrum which looks like this, that is from minus FM to FM. This point is M0. So, this is your spectrum MF in the frequency domain. Now, when we let us consider a modulated version of MT, that is MT cosine 2 pi FCT, which as we are well familiar has the spectrum half MF minus FC plus half MF plus FC, that is MF shifted to FC and MF shifted to minus FC. If you look at that spectrum, that is going to look something like this. First shift MF to FC, correct? You shift MF to FC and scale it by a factor of half. So, this height here is going to be half of M0. So, this corresponds to your factor of half FC, and if you look symmetrically on this side, you will have your half MF plus FC, that is shifted to minus FC. So, this is your half MF plus FC, and this is a spectrum, as I have already said, this is a spectrum of MT cosine, spectrum of MT cosine 2 pi FCT. Now, if we want to generate a single sideband modulated signal, all I have to do is high pass filter this with a cutoff of. So, I have to take high pass filter, cutoff of. So, this has to be a high pass filter and cutoff frequency equals FC. If you take this high pass filter cutoff frequency FC, that is which has response unity for all frequencies greater than FC and exactly 0 for all frequencies which are less than FC, and it has a sharp cutoff at FC. So, if I pass my DSB-SC, that is double sideband modulated suppressed carrier signal MT cosine 2 pi FCT through this high pass filter, I get the output is your, so this is FC, this is FC plus FM, and again once again this is half M0, and similarly on minus FC, this is going to be minus FC, this is going to be minus FC minus FM, and this is your SSB, correct. In fact, this is your USB signal, that is upper sideband modulated signal. This is the upper sideband modulated signal, and in fact to generate the lower sideband modulated signal you have to pass it through an ideal low pass filter with cutoff FC. Okay. And the problem that we have said in generation of this upper sideband modulated signal through this method, remember this method is the frequency discrimination method. If you remember this is this technique of passing it through this high pass filter, this technique is termed as frequency discrimination. Okay. Frequency discrimination for SSB generation. And the problem with this, or rather the challenge, is to generate high pass. The challenge of this to design high pass filter with such sharp cutoff frequency, that is in fact practically very challenging, if not impossible, because frequently no matter how well your filter is designed, it always has a small transition band. A transition band is a band in which it is transitioning from the zero, there is a stop band. Remember this band where it is 0 frequency is the stop band, pass the frequency band where it is allowing the frequencies to pass, that is gain of unity, is the pass band, and there is a small transition band, a finite transition band in which it is transitioning, the filter is transitioning from 0 to 1, and that gives rise to non-ideality. So, what happens is frequently we have your, let me just draw this thing over here. So, your high pass filter is, this is your FC, we need a sharp cutoff at FC, this is your ideal, and what we have is something that looks like this, that is, this is basically, so this is your stop band, this is the pass band, and similarly on the negative frequency side, if I have to draw this minus FC, the ideal one would be something like this, and what we would have is something that looks like this. So, this is your stop band, this whole area is your stop band where attenuation is 0 or very low. This area which is basically over here from here to here. So, this part is your pass band where the attenuation is equal to 1, but this part, if you look at this part where it is rising from 0, so here it is 0, here it is 1, and this particular part where it is rising from 0 to 1, and similarly over here if you look at this particular part where it is rising from 0 to 1, these two are the transition bands. Okay. So, where it is not 0 and it is not 1, but the filter magnitude response lies between 0 and 1, this is a transition band. Let me just write that with bold, so that this is your transition band. And this transition band, and what happens when you have this non-ideal filter, and basically you pass the same DSB-SC double sideband modulated signal, that is MT cosine 2 pi FCT, alright. When you pass it through this, that is of course you have something like this over here. So, you have, this is FC, this is your MF minus FC, that is shifted to FC. So, this is your FC, and this is your this is your minus Fc, and when you pass this, so this is pass through non-ideal HPF high pass filter with a transition band, and that gives rise to your signal which looks like that gives rise to the signal. So, that gives rise to some signal which is not exactly the upper sideband modulate, which does not. So, it has something which looks basically like. So, if you look at, if I were to draw this signal approximately, so this is Fc, so it would be something that looks like this. It picks up a small. So, what we have is, this is your Fc, this is your Fm. What we have here is a small vestige of your lower sideband. Okay. And similarly, over here when you pass this through your this non-ideal high pass filter, what you pick up is basically something that looks like this. This is a vestige of the vestige of the lower sideband. This is basically your non-ideality. Or the impact of non-ideality. So, this is your, what is it? This is your now. So, what you have is basically, because you are passing this through a non-ideal filter, high pass filter, which has a small transition band, that is, it is not exactly 0 for f less than Fc and 1 for f greater than Fc. It has a small transition band where it is transitioning from 0 to 1. It picks up a small portion of the lower sideband. This small portion is termed as a vestige. A vestige is typically means, in English it means a small portion, a small piece. So, it picks up a vestige of the lower sideband, hence this is termed as vestigial sideband modulation. So, this signal, which is basically not exactly, so this signal is termed as your or let me just again write it in bold. Let me just write it in bold. This signal is termed as your vestigial VSB, which picks up where the which contains a vestiges of the other sideband. So, which contains, for instance, the upper sideband contains a vestige of your lower sideband. Ideally, it is not supposed to contain any part of the lower sideband, but because of the non-ideality of the filter, it contains a small portion or a vestige of the lower sideband. This is termed as vestigial sideband modulation. Alright, and the advantage of this, of course, it is non-ideal. Now, the point here is, look at this, it requires a slightly higher bandwidth than the upper sideband modulation, because if you look at the bandwidth that is required, USB signal requires a bandwidth of only your FM, correct, passband bandwidth of FM, which is of course half that of the DSB, which requires passband bandwidth 2 FM. However, this requires a slightly higher bandwidth FM plus, if you call this FC minus FV, F vestige. So, this requires a bandwidth of, because of the vestige you require, because of the vestige, that is small portion of the requires a small portion of LSB. So, net bandwidth of the signal equals Fm plus Fv, where Fv remember is the bandwidth of the vestige. Fv equals bandwidth of the vestige. So, if you look at this, therefore, now remember DSB-SC, double sideband modulated suppressed carrier, has a bandwidth of 2 FM, which is greater than your vestigial sideband modulation, which has a bandwidth of Fm plus Fv, okay, which is greater than the bandwidth of your single sideband modulation or upper sideband modulated signal, which has a bandwidth of Fm. Therefore, if upper sideband modulation, that is single sideband with upper sideband, that has simply bandwidth of Fm, which is less than Fm plus Fv, the bandwidth of vestigial sideband. Therefore, it is more efficient than vestigial sideband modulation, which is in turn more efficient than double sideband modulated suppressed carrier. So, this is basically increasing spectral efficiency from double sideband this is increasing. So, you can see that vestigial sideband modulation is a trade off, it is a trade off. It has a bandwidth efficiency or spectral efficiency that is less than that of upper sideband modulation, but more than that of double sideband suppressed carrier. However, it offers an advantage, that is it has a much lower complexity in comparison to your upper sideband modulation, since designing these filters, this non-ideal high pass filters, it is much more easier compared to the designing of the ideal high pass filter with upper sideband modulation. Okay. So, however, VSB has lower complexity, meaning the implementation complexity of implementation in comparison to USB, since it does not require ideal high pass low pass filter, ideal high pass filter. Similarly, since it does not require ideal high pass filter, similarly one can think of a vestigial sideband modulated signal with a lower sideband transmitted and picking up a vestige of the upper sideband. Okay, so both these things are possible in vestigial sideband. Either you can have what we have shown here is a non-ideal high pass filter with the upper sideband and a small vestige of the lower sideband, but analogously you can also think of a non-ideal low pass filter which transmits the lower sideband and a small vestige of the upper sideband. Okay, so both these things are possible, but since they are similar, we will just restrict our discussion to the case of vestigial sideband modulation with the upper sideband modulated and the vestige of the lower sideband. Okay, so that is the first point. So now the other thing that we have to talk about is basically this is your vestigial sideband modulation. So because of the slightly larger bandwidth, it is slightly lower spectral efficiency compared to upper sideband modulation, but it has a lower implementation complexity. Now let us look at the properties of the VSB filter. So what we would like to do is let us look at the properties of the VSB filter. Okay. So, we would like to look at the properties of the VSB filter. So, what we will do is, since we have already covered some aspects of the VSB in this module, that is an introduction to VSB, and also described the basic functioning of the VSB and the spectral efficiency, we will end this module here and we will look at the properties, that is how to exactly implement this vestigial sideband modulation and what property the non-ideal high pass filter has to satisfy. We will look at that in the subsequent module. Thank you.